Okay, I think we can start. Let me prepare my list of questions. Okay. Welcome to seminar Geometry, Arithmetic, and Differential Equations of Periods. Today we have our guest Michel Waldschmidt. We have a conversation with him. I don't like to tell interview. I don't know. The word conversation seems to be a better word. Anyway, so thank you, Michel, for accepting the invitation. So let's start. So first question, maybe I would like to pose about your first mathematical experiences. They are fostered by which people, and your first teachers in mathematics, who they were, and okay.
Thank you, Wayne. So thank you very much for starting this process and suggesting me to discuss with you during this afternoon. And I will try to answer to your questions. And the first one, I like it very much because my first mathematical teacher was, in fact, my father. When I was young, I had some small exercises to do, like with a train going on and back. And so we asked our father to help us. And he was taking a piece of paper, writing something which we did not understand. And then he explained the solution in a very simple way. And in fact, he knew algebra, which was fascinating for me. So he was really my first teacher. He could have been a good mathematician, but he did not have the opportunity. His father, my grandfather, passed away in the French army in 1914. And so my grandfather was killed, and my father was just 1 year old. So I have a lot of sympathy now for the pacifists like Bertrand Russell. But after that, my next teacher was called Monsieur Chipon. It was in the high school, and it was during the 3 last years of high school. And I liked very much the geometry. We were using some complicated figures and equality of triangles. And it was a lot of fun to solve these challenges. I must say that nowadays, all what was interesting in this time in the high school disappeared from the program because the official people say that it was too complicated. And so nowadays, what is taught in the high school is no more interesting because it's too easy. Fortunately, there are some activities like the Kangaroo of Mathematics or Animat, which take care of that. At the same time, during this high school, there was some optional course on what was called modern mathematics, which was just the set theory, bijective math, and so on. But it was something which was completely separated from the geometry and the normal courses. I did 9 years in this lycée Henri Poincaré. In fact, this is Nancy, my home place, is the place where Poincaré was born in 1854. And in fact, Poincaré himself was in this student in this lycée impérial, as it was called at that time. After that, I went to the university in Nancy again, and I had many good professors like Pierre Aymar, Madame Hervé. But in fact, you may know that Nancy was a place, in the golden age of Bourbaki. There were many people in Nancy from the Bourbaki group. There was Veil, Dieudonné, there was Serre went there, and also Paulo Ribbenboim came there. So I was there in Nancy at the right time, but not at the right age for me. I was too young. I could not benefit from them. And Delsart was one of the founding members of Bourbaki, and he invited a professor, a colleague of him from Japan, Shokichi Yanaga, who came for 1 year, and he gave a course which was supposed to be a course of algebra, but in fact he gave a course of number theory. It was the book of Samuel on algebraic numbers, and this was called a course of algebra. I liked it very much, and so I said to my professor, Pierre Aymar, I would like to study algebra. And Pierre Aymar told me, oh, algebra in France, is not, there are not so many places, but you could apply to Bordeaux. So I went to Bordeaux. And in fact, in Bordeaux, there was a group of number theory, and I discovered that what was taught to me as algebra was number theory. And this is how I became a specialist in number theory.
Right. Okay. And then what was your first mathematical feeling of discovering mathematics, that you felt that you are creating something new in mathematics?
When I arrived in Bordeaux, the assistants were supposed to attend the weekly seminar regularly. And so I did it. At the beginning, I did not understand almost anything. And at the end, I understood a little bit. And I remember once there was a talk on non-commutative algebra. There was a problem which was asked, and I solved this problem. I have no idea now what it was, but I was very proud that I could solve some problem which was asked and not solved by the speaker. But my first discovery in mathematics was in June 70. I was working on something which is called the first problem of Schneider. Maybe I will tell you more a little bit later. And I thought I had a proof, and I found that there was a mistake. And so this happened many times in my life. And so then I had my first flash. I found just suddenly a few days later that the proof which was not working for the first problem of Schneider was working for the 8th problem of Schneider, so another problem on which I was working. So this was really a very good feeling for me to find that I had a new result. And so I was very glad of that. I published it in the Journal of Number Theory. And as a matter of fact, in the same issue of the same journal, another paper was published, and the editor did not know that there were the two papers on the same topic, on the same, exactly the same proof of the same result. And it was done by Dave Brunawell. So often in mathematics, what happened in this case that the two mathematicians who are in this position get rivals, but it was not the case with Dave Brunawell. We are good friends for that from that time on. And so when I found the proof, I said to Fresnel, well, in fact, I just used tools which were known. I did not invent anything. And I thought that a new result needs a brand new method. And Fresnel told me, no, it's okay. It's like this that it works. So I mentioned the flash which I had. It is something which is described by Poincaré and also by Alain Cohn in a book with Jean-Pierre Changeux, Matière à penser. And they explain how the brain is working. And it's quite interesting that we work a long time on the problem, and then we just find the solution when we think to something else. And I had my second flash 10 years later, when I was brushing my teeth. I remember very well. I had a working group with the two students of mine, Ressa and Philippon. We were working on the problem of Chudnovsky. And I told them that they could use a method which I had developed with Mignot. And they did it, and they published something using this idea. And then the next day, I found that this idea that I suggested to them was exactly what was needed for the problem on which I was working for 10 years. And so I was very glad of that. It's interesting because when I found this solution, I knew that I had the solution, but the proof was not complete because I needed some auxiliary lemma. I was sure that it was true, but I did not have the proof. And David Marcer was in Paris at that time giving some lectures precisely on this subject. And I asked him whether he could extend his method to prove the lemma which I needed. And he said, oh, yes, of course, I can do that. So he published the proof of the auxiliary lemma which I needed, which is a fundamental result, zero estimate. And then I published my proof.
Okay. This was before your PhD thesis?
No. In fact, you see, at that time, the situation was quite different from nowadays. When I got a permanent position, I did not know what was research. I just had the master, or the equivalent of the master. And then I became immediately assistant professor with a tenure, and I got my PhD in 72. And at that time, it was much faster than nowadays.
Okay. So talking about PhD, then You did in transcendental number theory. How did you came up on this topic? I mean, number theory is big, and specifically, why transcendental number theory?
Yes. So this is really the beginning of my research. When I came to Bordeaux, I was asked by some professor there, do you want to do research? And I said, yes, of course. I was a bit afraid whether I will succeed or not. But and one professor there asked me, okay, you could look at the numbers, the prime numbers of the form a squared plus 27b squared. And he did not say anything more about that. And I did not find anything. I had no idea of how to start. There is now, I know that there is a conjecture that prime number is of this form, a squared plus 27b squared, if and only if this number p is congruent to 1 modulo 3, and 2 is a cubic residue modulo p. But I had no idea of that. And then Fresnel came to me and told me, do you have a research topic? And I said, yes, but I am stuck. I do not have the least idea. And he suggested to me to work on a conjecture of Leopold, which was just 10 years old, and or no, 6 years old. And it was about the p-adic regulator of a number field. And it's an analog of Dirichlet's theorem for the unit of an algebraic number field. And he told me, this should not be so difficult. We just have to prove that some determinant is not zero. So just try to do that. And I must say that nowadays we do not know whether it's true or not. But anyway, he explained me, he helped me to start in research. And every afternoon on the Saturday, every Saturday afternoon, we work together during all the afternoon in the university. And each week, I explained him that I have a proof. And during this afternoon, he explained me that my proof was wrong, but he told me, he gave me some ideas to go further. And at the end of the afternoon, I thought, okay, I did not solve it, but now I think I should succeed. And the next week, he started again. So he started to help me using algebraic number theory. And then he said, oh, you should use either cohomology or transcendental number theory. At that time, Baker had proved just a few years before this result, and Brummer had translated it in p-adic. And this was important for the p-adic regulator in some cases. So Fresnel did not know which one I should look at, and I had no idea of what it meant, either one or the other. And finally, he told me, okay, just look at Baker's paper on transcendental numbers. This is what I did, and this is how I started with transcendental number theory. Many people who started at that time did it because of the work of Baker. This was really the main input to help people to work on Baker's method. And so it was quite hard to start with Baker's paper because they are very complicated. But I learned what was going on when I found sometime later the book of Lang, Introduction to Transcendental Number Theory. So for me, this was really how I understood the proof and how I could make some progress. When I published my first paper, I sent it to Siegel, and Siegel sent me a letter where he said, you are quoting Lang's book, but be aware that there are only 105 pages, but there are more than 100 mistakes, some of which are quite serious. But in spite of that, I think that Lang's book is very good to learn the topic and to see what is going on. The other authors like Schneider, Gelfond, Baker do not explain what they are doing. They just do it.
I see. Okay. So talking about transcendental numbers, so what is your favorite transcendental number if you want to choose one?
Okay, I have many of them. Maybe I will select 3 of them.
Okay.
The first one is somewhat a joke. It is Euler constant. I chose the first one because, well, first of all, it may be that the proof comes from the study of multiple zeta values. Also, because it is not known whether it's transcendental or not. And also because there is a paper which is published where there is a corollary saying Euler constant is rational. and the author thanks me to help him to complete the proof that it is rational. So the true story is that when I read the paper, which I will not say the name of the author, but when I read it, I found that the consequence of the theorem was that Euler constant was rational. And I explained to the author, there is a mistake, because if your result were true, it would prove that Euler constant is rational without giving the numerator and denominator. But nevertheless, the paper is published. But okay, this is my first choice. The second choice is a number which is a complex number. And again, it's a little bit cheating because it is exponential of e, the basis of the exponential, plus I times exponential of e squared. And so the reason is that to say that the complex number is transcendental means that at least one of the real part and imaginary part is transcendental. And this is the result which I mentioned, which was called the eighth problem of Schneider that I solved at the same time as Dave Brunawell. And the third number, which I like very much, and which is now a true transcendental number, is the gamma of Frankfurt. The transcendental gamma of Frankfurt was proved by Chudnovsky. And when I gave lectures on the proof of Chudnovsky in the Tata Institute of Fundamental Research, just after it was proved in '76, I said that the proof was not so difficult. And Ramachandra was quite upset. He said, it's just a beautiful result. You should not say that the proof is not difficult. I do not want to say something bad about the proof. It's just that when I saw the result, gamma of Frankfurt is transcendental, and the proof, I thought, oh, this should be a consequence of what I've proved. And it was not a consequence. I just missed it. And Chudnovsky was much clever than me. What I mean is that Chudnovsky had some other contributions which were very complicated and very deep. And gamma of Frankfurt for him was not the most difficult result that he has proved.
Okay, so maybe once in my class, I asked the students why many mathematicians they use this e and pi number, but they never need the approximated value of these numbers or if they are transcendental or not. What is your answer about this?
Okay, so your question has two aspects. First, for the numerical value, I will tell you some story about that. I taught a course in the university, Paris 6, which is now Sorbonne University. So I was teaching a course, and I got some letter from someone who introduced himself as a musician, a composer, Tom Johnson. And he told me, I am interested in number theory for composing music, and he did a lot of things with music. And I would like to attend your course on number theory. So he wrote a number of pieces of music using prime numbers, Fibonacci sequence, mathematics of juggling, block designs. And so he attended my course. And after a few courses, he came to me and told me, but is it really a course on number theory? And I said, yes, of course. But he said, I did not see a single number. I saw alpha, beta, x, y, and so on. But I did not see a single number. And he was right. I was looking at the abstract theory. And now I must say that thanks to that, I make some effort. And I try to give more examples to explain that number theory really deals with numbers. I must say that it may be a French influence, but when I attend when I participate to teaching in some schools, I find that my colleagues from other countries give more examples than me. So I am trying to make some effort. And of course, I visit India, and in India, I met, for example, some students who like to give the decimals of pi, and they challenge each of them to give the largest number. But okay, so this is just for the first point on the numerical values. Now for the transcendence, I am not surprised that people do not know. I do not blame people that they are not aware of the state of the art. The situation is quite complicated. We know that E and pi are transcendental. We do not know for Euler constant. We do not know for E plus pi, E pi, or numbers like this. So it's a bit tricky to know what is the state of the art. When I was teaching in Orsay in 72, 73, a colleague of mine asked me about the reference for the algebraic independence of E and pi. And I said, oh, we do not know. And I explained him why it is so difficult. And then I told him, but why do you ask me this question? And he said, oh, I need it. And then he explained me why he needed it. And in fact, he needed just 2 algebraically independent numbers. And I told him, oh, in this case, it's easy. I can provide you plenty of transcendental numbers. But he thought, okay, this should be the easiest case. And in fact, it turned out that this is the most difficult case. In the same direction, when Nesterienko proved that the numbers pi, exponential of pi, and gamma of 1/4 are algebraically independent, I just told this to a friend of mine who is not working in number theory, and he was laughing. He told me, why these 3 very peculiar numbers? And the answer is that there are so few results which are known that to achieve such a result is quite remarkable. So most often when people ask me whether some numbers are transcendental or not, I just say, we conjecture that they are, but we do not know whether they are rational or not. So in my first lectures, I started by giving the conjectures, and then I explained the state of the art. And people were very disappointed. They said, oh, probably you are not looking at the situation in the right way. You should just change your point of view. But the results are very far from what we expect. So I am not surprised that people are not aware of the situation.
Okay. Let's go to the next question. So in the webpage of the seminar, I have put a quotation from Poincaré complaining about the name period, which apparently Picard was responsible for the name period due to elliptic integrals, Abel integrals. And what do you think about the name period that we give to some numbers? Yeah.
Okay, so this is quite interesting. When I saw this quotation, I looked to find the paper where it is published. And the title of the paper is Sur les résidus des intégrales doubles. And indeed, this quotation is in the paper. But it's interesting to put this into the context of the paper. In fact, Poincaré explained one example where Picard used the name period, and he said that for this kind of integral, he objects. He says that he gives 2 reasons for which one should not give the name period to the special integrals that are considered. He said, d'abord, ces intégrales ne sont pas des constantes, so they are not constant. En second lieu, il y a une infinité de systèmes de variables, et chacun de ces systèmes donne pour l'intégrale une valeur différente. So there are several variables. So Poincaré complained that Picard uses this name for something which is not a number, which is called period in the paper by Poincaré. And in the next page, he says, le savant géomètre emploie dans ces 2 notes le mot de période avec la signification que nous lui donnerons dans la suite. So Poincaré uses the name period and with a meaning which is also used by Picard. So the name period, Poincaré does not object that we use the name period for what we call period now, but it's just in the very special situation that Picard used. What we call period in analysis is just when you have a periodic function, f of z plus omega equal f of z, and this occurs with the exponential, the elliptic functions, the Abelian functions, and all these functions satisfy differential equations. So the periods are given by integrals, and this is why they started to call the period some integrals, but some definite integrals. And I think that the name period, like we use it nowadays, comes from the paper of Kontsevich and Zagier, which was published in 2000, and they do not quote Picard and Poincaré. And at the end of the introduction, it is written, the last chapter, which is at a more advanced level and also more speculative than the rest of the text is by the first author only. So it's only by Kontsevich. Zagier does not want to take any responsibility for that. And in fact, for me, the first part is quite advanced. Just to prove the equivalence between the 2 definitions which are given in the paper, needed a Diplomarbeit in Leipzig in 2005 by Benjamin Friedrich, who wrote a paper on the period and algebraic de Rham cohomology. And it's not easy to see that the two definitions are the same. But anyway, the last chapter is called Periods and Motifs. And I like the last sentence of the paper. Then all constants, all classical constants are period in an appropriate sense. So now they transpose the definition of period to the transposition of what is a classical constant. And this is just the same problem which occurs. The goal is to define the class of interesting numbers. And we expect that interesting numbers will be a countable set. And we want to avoid the pathology. And for example, we expect that the classical constants are all Liouville numbers. But to give a precise definition of what is a classical constant is something which is yet something to be done. So there is a precise definition of a period. There are exponential periods at the end of the paper of Kontsevich and Zagier, and there is plenty of room to discover new periods.
Okay. So what do you think about using arithmetic algebraic geometry and machinery of schemes and the stacks in order to prove some explicit statements in transcendental number theory? Sometimes developing a general language makes the person far away from explicit problem. For instance, Grothendieck is famous for giving 57 as a prime number. So what's your opinion about this? If this balance between abstract and explicitness?
Okay, so when transcendental numbers started with Liouville and then Hermite, Lindemann, Weierstrass, Liouville constructed transcendental numbers, and then Hermite, Lindemann, Weierstrass were interested with the exponential function, which is a classical function. And Siegel went a little bit further with elliptic integrals, and Schneider continued with the elliptic integral of the first and second kind, and then the Abelian integrals of in 1940 when he proved the transcendence of beta of A and B when A and B are rational numbers. And for that, he needed to use the Jacobian of the Fermat curve. So the beta function is a classical function, but to prove something on the beta function, we need to use Abelian varieties. The subject developed with a meeting of Cartier and Lang in the Bourbaki seminar when Cartier suggested to Lang to extend the results on the exponential function from the classical case of the sum of Zn over n factorial to the case of algebraic group. By the way, Cartier once told me, no, Lang told me, that Cartier suggested another problem at the same time, which was related with Bessel functions. But neither Lang nor Cartier did remember what was the second suggestion. So they will probably something very interesting to develop, but we do not know what it is. So anyway, this is how the transcendence in the algebraic group started. So you see, it was progressive. First exponential, then elliptic, then Abelian, and then algebraic groups. So when I mentioned this in my course in the Collège de France, le cours PECO, I mentioned the fact that one of the problems of Schneider, the third problem, was about elliptic integrals of the third kind. And I said that we do not know the functions which are associated to that. And Serre told me, oh yes, they were known in the 19th century. And then the next week, when I gave the next course, Serre told me, oh, I did not find a reference, so I wrote for you the details of the construction of this function. And this is how elliptic integrals of the third kind came. We got some results on this. When the Becker's method was created, it was for the exponential function. But after that, David Masser developed it in the case of first the elliptic case and with elliptic integrals, and it was developed by Becker, Coates, Masser. And then the algebraic groups were used for zero estimate and for multiplicity estimates. And a lot of results have been used by Bertrand, Ressa, Laurent, Philippon, and it culminated with the work of Masser and Wustels, which use algebraic groups. So nowadays, algebraic groups are absolutely a very important tool in this domain. But this is not the last word. After that, it came with the contribution of Bost using Arakelov theory, where he used some more deep results from algebraic geometry. And this is a language which is more abstract. My students know it very well, like Daniel Bertrand, Stéphane Fischler, and the next generation, Yves-André Sinou-David. For them, for Yves-André, motifs are something quite natural, which is something not true for me. I mentioned that to Sinou-David recently, and he told me, what is good is to use the level of language in which you have some feeling, where your intuition works the best. And I think it's good, but I am convinced that the deep tools of algebraic geometry will enable to go further. And one good example is the work of Francis Brown, who uses motifs connected with multiple zeta values. And he is able to make the connection between the motifs and also the proof by Apéry, for example, which is something which is quite elementary without using any sophisticated language. And so if I were to give an advice to young people, it would be to learn the deep language, the high-level language, because I'm convinced that there are still many things to be discovered using the elementary method, like the one that I am used to use. But I think that the languages of high level will be more efficient and will give more results in the future. So I think it's a good development. But everybody has his own limitation. I remember when I discussed with Feldman, who got some very important and major contribution in transcendental number theory, but he had some difficulty to understand complex multiplication, which is something which is quite familiar to us. So everybody has his own limitation, and we have to deal with that.
Okay. So next question is, in the last 20 years, we have seen many interaction between number theory and physics, and in particular, mirror symmetry string theory. What is your opinion about this? Can you tell a few words about this?
Yes, I can say something. It used to be in the past that the interaction between physics and mathematics was very strong in some countries like Russia, and not so strong in France. It was probably the influence of Bourbaki, but this is no more true nowadays. For example, the IHES is at the highest level in mathematics and in physics. So my own connection is rather tiny. My interest in theoretical physics just comes from the fact that I have been invited by physicists to give some introductory lectures in multiple zeta values, because multiple zeta values is quite important in the theoretical physics. But I am not so much familiar with that, apart from the seminar which was done by Cartier some 10 years ago, a little bit more. Cartier is one of the mathematicians nowadays who has the broadest knowledge in mathematics, and it goes up to theoretical physics. So he started a workshop on the multiple zeta values, and there were many people attending it, like Jean Ecal, Louis Boutet-Monvel, Michel Petitot, Van Gogh-Min, Jacques Cresson, and many others. And Cartier gave a lot of lectures. For example, he spoke of the role of Feynman integrals. And this is essentially where I learned the subject. And after that, Cartier gave a course, advanced course in the IHP, Institut Henri Poincaré. And Francis Brown attended this course. And this is how Francis Brown started to work on the motifs and multiple zeta values.
Okay. So let's say there are many mathematical physicists who wants to remodel physics, not by real or complex numbers, but p-adic numbers. And even there are many mathematicians, for them, p-adic numbers are much more natural than real and complex numbers. What do you think about this phenomena?
Okay, so to remodel the world using p-adic numbers, I don't know many people who are trying to do that. I would say that for people working in arithmetic of Diophantine geometry, p-adic numbers is an essential tool. And for them, inside the subject, mathematical subject, yes, p-adic numbers are as natural as real numbers. But it's really a tool for people working in this direction. For the real world, if there is some other civilization, will the real numbers be replaced by p-adic numbers? I doubt it. Maybe later, you see, the Newton laws were using just real numbers. After that, with Einstein relativity, we use quantic theory. And will there be a development with p-adic numbers? I don't know. It depends on whether our civilization continues. Grothendieck said that the end of the world will be in 1982, so we are just waiting for that. But for number theory, p-adic numbers is an essential tool. We cannot deal without it. And my own work was on Leopold's conjecture on the p-adic rank of the unit of a number field. And we are lacking an analog of the geometry of numbers of Minkowski to prove the result. And so for that, we have to develop the p-adic transcendence. And one of the pioneers on this topic was Kurt Mahler. He really started the topic. And there is an important contribution of Serre on the dependence of p-adic exponential, who developed the transcendence method because he needed them for L-adic representations. So in mathematics, p-adic numbers is essential, but in the real world, I doubt it.
So can you tell us about the role of differential equations in number theory? Few words about this.
Yes. In the 19th century, at the end of the 19th century, the results which were known were on the exponential function of Hermite, Lindemann, Weierstrass. And there was also in 1900 the seventh problem of Hilbert on A to the B, A and B algebraic. And there was a dream of Weierstrass, which was to have a general result saying that if you have a transcendental function, usually at an algebraic point, it takes a transcendental value. Usually, we have to avoid some examples. For example, for the exponential function, we have to avoid the point z equals 0. But very fast, Weierstrass found himself some counterexample, and now we are able to construct some function which take transcendental values at transcendental points, and they send any algebraic number field into itself, and they are transcendental functions. So there is no general result like this. And so it's a kind of pathology, but now the question is to know which function we should take. And it turned out that to use differential equations is a very good way to get some general results. It started with Siegel and the theory of E functions, where he extended the method of Hermite and obtained some results on Bessel functions. And then there was a criterion of Schneider, Lang, Bombieri, where the main assumption is that the functions satisfy differential equations. So differential equations are a very nice hypothesis to get some very good results. But this is not the end of the story, because there are some functions which do not satisfy differential equation and which are quite interesting in mathematics, in number theory. For example, Mahler introduced a method which uses functional equation, not differential equation, but functional equation. And the function of Mahler are very important in the world of combinatorics, partition theory, finite automata, theoretical computer science. And we know that they are hyper-transcendental, so there is no differential equation at all. So one question is whether the special values are periods or not. Are they classical constant? This is an open problem to be discussed. One of my main problem was the 4 exponential theorem, and we know a partial result, which is the 6 exponential theorem. We do not know the 4 exponential conjecture, I should say. And in the proof of the sixth exponential theorem, we do not use a differential equation. When Baker introduced his method, differential equations were very important. It was essential. But it's possible to prove Baker's theorem without using differential equation by extending the method of Schneider to solve the Hilbert's seventh problem. There were two solutions, one by Schneider and one by Gelfond. Gelfond used differential equation and not Schneider. So it's possible to extend Schneider's method in several variables and get Baker's method. So differential equations are very efficient, but it's not a universal tool. There are some other methods, other assumptions which are sufficient to prove the transcendence result, and which gives some very interesting result also.
Yeah. Okay. Okay. So let me see. Okay. What has been your obsession in mathematics? Which problem or conjecture you tried a lot, but you failed?
Okay, there are many. I selected the three examples. The first one is the four exponential conjecture. It is the fact that if you have algebraic numbers, alpha 1, alpha 2, alpha 3, alpha 4, the product log alpha 1, log alpha 2 will be equal to log alpha 3, log alpha 4 only in trivial cases, like log alpha 1 over log alpha 3 is rational, or log alpha 1 over log alpha 4 is rational. So this is the so-called four exponential conjecture. You see logarithm and not exponential, but we can translate it and have exponential. I spent a lot of time to work on that. And I can say that I solved this problem many times, but the same number of times I found a mistake. So it's still an open problem. It's a special case of the problem of algebraic independence of logarithm. Baker solved the problem of linear independence over the field of algebraic numbers. And the problem of algebraic independence is widely open. I worked with Damien Roy, who proved a lot of very interesting results in this direction, and he has an approach to even to the conjecture of Chanuel, which is very promising. We got some results on quadratic relations, but not on the four exponential theorem. And the question which I would like to see the solution one day. And I don't know whether the problem will come only for the four exponential conjecture or for the algebraic independence of logarithm, which is more general, or for Chanuel's conjecture, which is even more general than that. And maybe the solution will come from the general conjecture of Yves André on motifs, and then everything will fall as a consequence of the general proof. What will be the solution? I have no idea. I will be interested to see it. The second problem was the Lemmer problem on the low bound for Mahler's measure. I spent quite some time on that, but without any result. I did not. For the first one, the four exponential, I published some papers. I got some partial results. But for the second one, Lemmer's problem, I never get anything. I just published a survey and that's all. And for the last example, which is multiple zeta values, it is the same. I published several surveys on that, some introduction, but I find the subject fascinating. I spent a lot of time to find something new, and I did not get anything new. I gave some course in India on this topic. It was an introductory course, and Joseph Oesterle went in the same place and gave some advanced lectures. And then he had some good students, and they produced very nice papers. And so this means that there were some very good research subject to be found in this domain, but I did not find them myself. But I am glad that the subject is progressing from so many different points of view: elementary, combinatoric, analytic, and motivic. So it's very interesting to witness the development.
Yeah, okay. So you had many administrative tasks in the past, and in the same time you have not stopped giving lectures and doing research. Maybe tell us about how you managed to do all these together.
Yes, to tell the truth, during almost 9 years, when I was president of the French Mathematical Society from 2001 to 2004, And then I was deputy president of the CIMPA, the Centre International de Mathématiques Pures et Appliquées, from 2005 to 2009. I essentially published survey papers. I did some research. As I told you, I worked a lot on multiple zeta values without any new contribution. But I did not really find some important new result during that time. I had a lot of activities earlier, and I resumed in 2010. So to tell you about the previous part, when I started to have an academic position, it was in 1968, the teaching load for the professors was 3 hours per week. The professors had plenty of time to do research, and they have also a little bit for administrative duties. A very small number of these academic people use their free time to have other activities, for example, for teaching to get more money, and so they were not really supposed to do so, but it was not against the law. And what happened is that in 1982, a new director of higher education and research in the Ministry of National Education was appointed. His name was Jean-Jacques Payan. I knew him because he had contribution in algebraic number theory, which were close to my initial studies on the p-adic regulator and Leopold's conjecture. And when I learned that he was appointed, I was quite glad. But it turned out to be terrible because he considered that one should not allow academic people to behave like the small minority that I just mentioned. And he started by saying that those who were not active in research should teach more, which may look reasonable. But this is what we call the bad good idea. The output was a disaster. The new law increased so much the teaching load of everybody that it has a very negative consequence on the availability of people to do research. Now, I must say that for myself, I did not have a too heavy teaching load, especially at the end of my active teaching period until January 2012, when I became emeritus, because there was an agreement with foreign universities and my university, which was Paris 6 at that time. And part of my teaching duties were done in remote places like Cambodia, Vietnam, Nepal, India, and Brazil. And this is how I came to IMPA in Rio in 2010. And as a matter of fact, it is the place, Rio, where I started to resume active research after I had completed my official duties. What happened is that Claude Levesque was visiting IMPA at the same time as me in 2010. And he suggested, when we were working in Rio, he suggested to me a problem on families of Diophantine equation. And when he mentioned this problem, I told him, well, what is known on that? And he said, essentially nothing. And so we started to work together. And we wrote more than 10 joint papers on this topic. I knew Claude for many years. We discussed a lot, but never we started to do research. And this is how I started to do research again. Oh, your microphone.
It is raining in my my microphone.
You have the picture, yes.
So my feeling is that in the less developed countries, due to many reasons such as bad conditions of research, low salary, etc., one loses motivation to do research in pure mathematics. As a person who is widely active in the promotion of science in these countries, what one has to do further in this direction?
Yes, you're right that there are many reasons for the situation. And when a problem is complex, I don't believe that an easy solution will provide a complete answer. So I will just mention 2 points. The first one is, why is it important to have strong mathematicians doing fundamental research in all countries, including developing countries? And the second point is how to reach this goal. So for this first point, it's clear that the developing countries need a lot of things like food and basic education. They need also higher education and higher mathematics. For example, to prepare the teachers we need to have people at the higher level who teach them the basic of mathematics. And many people agree that to teach applied mathematics, to have research in applied mathematics, in statistics, in didactics, is okay. But from my point of view, it does not suffice. It's not sufficient. I would like to take an example with the CIMPA, the Centre International de Mathématiques Pure et Appliquées. This CIMPA organizes some school, we call summer school or whatever, research schools. And there was some discussion inside the CIMPA when there was some proposal of teaching the Lefschetz formula, trace formula, Riemann-Roch, Atiyah, Hirzebro-Zellberg work on non-commutative geometry in the school of CIMPA in some developing country. And some people say, no, this is not for them. They just need applied mathematics or statistics. And it's not good to say that. It's not good to say that there is a level to which these countries are limited. We should allow them to have experts of all levels, including the highest level. And I feel that it is very important in developing countries to have academic people who participate to international networks. So we need them at all the levels, not only the basic ones. Now, how to reach this goal? I have no solution for solving all the difficulties like the one that you mentioned, the bad condition, the low salary. But I believe that improving education in developing countries will have a positive contribution. As a member of the CIMPA, which I already mentioned, of the Committee for Developing Countries of the European Mathematical Society, and the Commission for Developing Countries of the International Mathematical Union, I meet many colleagues who are committed to the improvement of mathematics in the least developed regions of the world. There were many mathematicians in ancient civilization in several places. There are talents all over the world. And I feel it is unfair that because of the location of their birth, so many bright young people are not able to develop their skills. Even if the program like the GREAT program, Graduate Research Assistantship in Developing Countries of the IMU, may be a drop of water to put out the fire, like in the legend of the hummingbird, let us do our bit.
Yeah, okay. So we came to the last question, which is a kind of canonical question too. If you were to start a new career, what you would choose in mathematics or even science or art? What would be your plan for the future?
Okay, so when I was young, I was good in mathematics. I was not among the best one in my class, but in mathematics, I had good marks. And that was essentially the only topic where I had good marks. I am very bad in handworks. My ancestors were artists. My father was a very good drawer, and my grandfather also was working in Nancy in what is called the Art Nouveau modern style at the beginning of the 20th century. And they were very good in the art, but I am not good at all. So in fact, when I was young, I had no choice. Math was only the only subject which I liked and where I succeeded. So I have been lucky to have Fresnel to help me to enter the topic of transcendental number theory. And it was the right time because the method, there were plenty of room for developing the method. And it suited me very well. It was exactly the kind of topic where I could succeed. And I do not imagine any field where I could have had the same success. So from this point of view, I have been very fortunate. Nevertheless, there is, so my answer to your question is that I think I would choose transcendental number theory again if I had the choice.
Okay.
Of course, it's a little bit illusory to imagine that we could go backwards, but nevertheless, there is one direction where I could have done better. I mentioned to you that I am not fluent in algebraic geometry, which is a shame in the country of Grothendieck.
I see.
I would feel that I should have done otherwise because I spent all my time developing the method of transcendental numbers and I have no time to learn the algebraic geometry. But I missed an opportunity because I was assistant in Bordeaux when Fresnel was teaching algebra, and he wanted to learn scheme theory. So he decided that the course of algebra will be scheme theory, and he asked me to give the course on introduction of to schemes by MacDonald. So I gave the course, and Fresnel gave the exercises. But I did not pursue. Fresnel pursued and did a lot of things with Van der Poot, for example, his book on the rigid algebraic geometry. But I did not pursue this language, and probably I missed an opportunity.
Okay. Amazingly, we were able to finish the interview exactly in 55 minutes.
Okay.
So let's the people, the audience has some questions. Still, it is getting recorded. If you want to keep your question for the non-recorded one, that would be okay also. Question? Okay, maybe I stop.
Thank you very much, Michel. Très bien, merci pour l'exposé qui était vraiment instructif et instructif.
Okay, so maybe no question. Okay, maybe I stop recording. This is the official part. Maybe the people are shy. Just a moment.